Hello class. In this video, we review for exam 2. 25 questions on the review. Let's see the first question. An initial investment amount P, an annual interest rate R, and a time T are given. Find the future value of the investment when the interest is compounded annually, monthly, daily, continuously. Then find the doubling time T for the given interest rate. So the original investment, which is called the principal, in this case is $250. The annual interest rate is 2.94%. And we need to know how to convert this percentage to its equivalent decimal. Divided 2.94 by 100. So R equals 0.0294. T is 15 years. So we have the following 5 parts to complete. I'm going to show you how do we use a TI-84 calculator. I think the basic scientific calculator would work as well. The fast way, I think, to process this problem, okay? So I would start with the annual interest rate R. Part A, the interest is compounded annually. So I'm using the annual interest rate, which is 0.0294. I think it's a good idea to write down the decimal on your scratch paper, 0.0294. So we start with the annual interest rate, 0.0294, and then I add 1 on it. Okay, annual interest rate plus 1. What is that? That is the compounding factor. All right? And I'm gonna raise the compounding factor to an exponent. And what is the exponent? The exponent is the number of times the interest is compounded over the lifetime. Over the 15 years, right? Since the interest is compounded annually, means once a year. So 15 years, 15 times. So we're going to raise the compounding factor to the power of 5, right? And then we multiply that by the principal, which is, I remember, $250. Just double check. $250. Okay? And the rounding rule, round to the nearest decimal, cent, nearest cent, of course, 2 decimal places. So our answer is going to be $288.98 because the 5 is bigger than or equal to 5. 288.98. 288.98. Right, that makes perfect sense. You put in $250. This interest rate is not very high. Over 15 years, you have more, like $38 each, right? $39 each more. Okay, part B, same thing, but this time in part B, the interest is compounded monthly. Okay, compounded monthly, and we'll still start with the annual interest rate, which is 0.0294. Yeah, one advantage of TI-84 calculator is you have your history here, just in case you need it. So remember, this is the annual interest rate, okay, 2.94%. And part B, the interest is compounded monthly. So we're going to divide the annual interest rate by 12. And what is that? And that is a monthly interest rate. Annual interest rate divided by 12 gives the monthly interest rate. And then I add 1 to the monthly interest rate. That gives me the compounding factor in part B. Okay, monthly interest rate plus 1. That is the compounding factor in part B. And I'm going to raise the compounding factor to an exponent, the exponent here is going to be the number of times the interest is compounded over the 15 years. 15 years, we have 12 months for 1 year. So it's going to be 12 times 15. Okay, why is that? The interest is compounded monthly, means once every month. So 12 times a year for 15 years. So 12 times 15. All right. And then I'm going to multiply that by the principal, which is $250. So if the interest is compounded, let me double check. This seems a little bit too high. 0.0294 divided by 12 and add a 1 and raise to the power 12 times 15 and then times 250. Okay. I know what happened. I made a mistake earlier. Here it's supposed to be 15. I think I typed it wrong. So let me redo part A, okay? Sorry about that. So part A, I'm start with the annual interest rate, 0.0294 annual interest rate plus 1. That's the compounding factor. And raise the compounding factor to 15. I intended to enter 15, but I made a mistake. I apologize. And then multiply that by the principal 250. And this time sounds good. Yeah. 386.10. Okay. And the monthly compounded monthly is 388.36. Okay, that looks right now. Yeah. It is higher than compounded annually, but not with very significant amount. It's higher, but not a lot. That's part B. Part C. This case, the interest is compounded daily. Same thing, okay? We're going to start with the annual interest rate, which is 2.94%. As decimal is 0.0294. All right, that's the annual interest rate. Divide the annual interest rate by 365. That's the daily interest rate. Okay, annual interest rate divided by 365 is daily interest rate. It's understandable because there are 365 days in a year. And add 1 to the daily interest rate, we have the compounding factor in part C. And I'm going to raise that to an exponent, and that exponent is going to be the number of times the interest is compounded over the 15 years. Since the interest is compounded daily, so 365 times a year for 15 years. And then multiply that by principal 250, and the future value of the investment is $388.56. It's a little bit tiny bit higher than part B, right? 388. 388.56. All right, part D. The future value of the investment when interest is compounded continuously. Okay, continuously use different formula. Let me show you how do we get it done in the calculator. We can start with the principal and then multiply the principal by e to the power r times t. R is the annual interest rate, so 0.0294 times 15 years. Okay, so for continuously, compounded continuously, the formula is principal times e to the power of R times T. R is the annual interest rate, T is 10 years. It's $388.57. A bit higher than daily, right? 57 cents. That's 56 cents. This is 57 cents. Okay. Part E. Find the doubling time for the given interest rate. You may use a different formula, but this is the formula I use, okay? I use continuous formula A equals, A is the accumulated balance, PE to the power RT, okay? Doubling time, we're looking for doubling time. What is doubling time? Doubling time is the time it takes for the investment to double. So we want to find the value of T such that when the time elapses, the future value is twice of the principal. Okay, originally $250. After T years, you want to have $500, right? So we cancel P here. The principal, we have 2 equals E RT 0.0294. And then we're going to solve this exponential equation. We're going to solve this exponential equation. Take ln on each side. And this cancel, right? And we have 0.0294t. On the left side, we have ln 2. Divide each side by 0.0294. 0.0294. We have t equals ln 2 over 0.0294. Zero 0.0294. Let's see how do we round it. 2 decimal places. 23.58. $23.58. Let me double check my work here. Doubling time. So 2 ln 2 over the annual interest rate. 0.0294. Yeah. Okay. So it takes like 24 years to double if the interest compounded continuously. All right. So we have an activity in the Blackboard related to this problem. You should see the activity before you see the review. Let's continue here. Next. Question number 2. Given ln 3 equals 1.0986, find the value of the following logarithm without using a calculator. Okay, without using a calculator. You need a formula, right? You need to know the product rule for log function. It is log with base b, x times y, equals log with base bx plus log with base by. I hope you still remember this formula from pre-calc. With that said, ln 3 times e can be expanded as ln 3 plus ln e. And then we know ln e equals 1 for any logarithmic function. If the base and argument are identical, then the log value is 1. So we have ln 3 plus 1. Okay, ln 3 plus 1. ln 3 is given. So the answer is going to be just adding 1 to the value of ln 3. It's going to be 2 points. It's 1 point, right? So add 1, you're going to have 2 points. 0.986 2.0986. All right, next question number 3. Use natural logarithms to solve the equation. This is an exponential equation. E to the power of negative 0.161 t equals 2. So we're gonna apply ln on each side, okay? By the power rule, this exponent can be brought in front of ln e. Then we have negative 0.161 t times ln e equals ln 2. ln e equals 1. We talked about this just in the previous problem, right? So it's 1. Then we have negative 0.161 t equals ln 2. And then we divide each side by negative 0.161, negative 0.161. We have t equals ln 2 over negative 0.161. So how do we put this in a calculator? We do ln 2 divided by, very important, this is not negative, okay? You want to enter negative, you do this one in the parentheses. Negative 0.161. 0.161. Close the denominator. Okay. Sometimes I use the parentheses just to make sure the the calculator is clear about the structure of the expression I want to tell it. ln 2 over negative 0.161. Let's see how do we round it. Round to the nearest thousands, so 3 decimal places. 305. 94.305. Where is the box? Oh, it's right here. Negative 4.305. Next. Question number 4. Solve the equation. Okay. Those questions are more like pre-calc problems. 20 e to the power of 2k equals 60. For solving for k, I would firstly get rid of the coefficient of the exponential function. We have e to the power of 2k equals 3, right? And then we're going to apply ln on each side. And we're going to bring 2k in front of ln e. We have 2k times ln e equals ln 3. One more time. Again, ln is 1, okay? ln is 1. So we have 2k equals ln 3. Divide each side by 2. We have k equals ln 3 over 2. K is ln 3 over 2. So this one we do not need to use a calculator because the question requires to type an exact answer. That means you have to type in ln 3 over 2. ln 3 over 2. Like that. Next. Question number 5. Solve x. This is a logarithmic function, equation. Okay, 3 ln x equals -9. Divide each side by 3 to isolate the logarithmic function first. And we have ln x equals -3. And knowing ln means that the base is e. Okay, so how do we convert this equation which is in the logarithmic form right now, to its equivalent exponential form. You remember the formula? I hope you do. Log with base bx equals y is equivalent to b to the power y equals x. That is something we learned from pre-calc. So b to the power y equals x. The base to the power of log equals argument. So with that formula, use that formula, we have e base to the power of log, this one is the log, equals argument, which is x. So x equals e to the power of -3. Okay. This one asks to run to keep 3 decimal places. So we're gonna have to use a calculator to evaluate e to the power of -3. E to the power of -3. Again, use this key for negative sign. Keep 3 decimal places, 0.050, because 7 is bigger than 5. 0.050. 0.050. Double check. Okay, next. Question number 6, differentiate. So if you know this formula, it will make your job a lot faster. E to the power of kx, the derivative of e to the power of kx is e to the power of kx times k. Just multiply the original function by the coefficient of x in the exponent. If you know this, you make your job a lot easier. Otherwise, you would use the chain rule. So we can prove this formula by using chain rule. If y equals e to the power of kx, we can let y equals e to the power u equals kx. dy du is e to the power u, du dx is k. So dy dx equals dy du times du dx. That gives e to the power u times k, which is k times e to the power u, which is kx. Right? Okay, assume you understand that, and knowing this formula, we're going to use that formula. So we're going to have, keep the coefficient 8, and keep the exponential function e to the power of 7x, and then multiply 7 in front. 7 times 8 is 56. So the derivative is 56 times e to the power of 7x. e to the power of 7x. That's it. Next. Question number 7. Differentiate. Okay, x to the power 4 is a power function, right? So that gives the derivative of 4x to the power of 3 minus, and this is similar with earlier, right? 7 times 9, 63, e to the power 9x, 9x. Let me double check. That's correct. Next. Differentiate. So this is, let's use the chain rule because the exponent is quite complicated. Let's write the original given function as y equals e to the power of x cubed plus 10x. Since the exponent on the shoulder of e is so complicated, it's very natural that you know to use u to substitute for that. Let u be x cubed plus 10x. Then y equals e to the power of u, okay? And then dy du is e to the power of u, du dx is 3x squared plus 10, and dy dx equals dy du times du dx. dy du is e to the power of u, du dx is 3x squared plus 10, So we have, it's good to, it looks prettier if we write the 3x² plus 10 in front of e to the power u, which is x cubed plus 10x, right? If you know the formula for this one, actually it's make your job easier. E to the power f is e to the power f prime. Okay, so the answer is going to be the derivative of the exponent, which is 3x squared plus 10, and multiply that by e to the power of x cubed plus 10x. Three x squared plus, okay, same with our answer here. Next, question number 9. We can use chain rule for this one as well. Let y be rule u. Okay, then u is the radicand under the square rule, e to the power of x plus 2. dy du equals 1 over 2 rule u. So I'm going to tell you that you should remember this formula because it is so commonly used. You should use this, you should memorize this formula. You should memorize the derivative of rule x is 1 over 2 rule x. So with that formula known, you would know dy du is 1 over 2 rule u right away. And du dx is e to the power of x plus 0. So dy dx equals dy du times du dx. dy du 1 over 2 rule u times du dx e to the power of x, and that gives e to the power of x over 2 rule u, which is e to the power of x plus 2. This is the answer you're going to enter in the cell. Oops, sorry. That's it. Next. Question number 10. Differentiate x cubed times ln 5x. We have y equals x cubed times ln 5x. I think I'm gonna use a product rule. So I'm gonna let f be x cubed, g be ln 5x. The original function is the product of the two functions. F prime is 3x squared. G prime is 1 over x. How do you know that? Ln 5x, you can use chain rule, okay? Yeah, I can show you how we do chain rule. If y equals ln 5x, you can do y equals ln u is 5x, dy du is 1 over u, du dx is 5. So dy dx equals dy du times du dx. That's 1 over u times 5. And u is 5x. The 5 cancel this 5, so it's 1 over x. Okay? So you can rewind if you needed this part. So g prime is 1 over x. So the derivative of the function equals the derivative of f times g, which is f prime g plus f g prime. That equals 3x squared times ln 5x plus x cubed times 1 over x, okay? So f prime times g plus f times g prime, and that gives 3x squared ln 5x plus x squared. X cubed over x is x squared. So this is the answer in the entry itself. I would use parentheses. I think if you do not use parentheses, I think use parentheses definitely will not give you a wrong answer. Without the parentheses, in this case, it's okay. Plus x squared. Double check the entry. That's it. Next. Differentiate. Okay, 切入 again. We let y outside function ln u, inside function u equals x 6 power over 5. dy du is 1 over u. du dx equals coefficient 6x to the power 6 minus 1 is 5. So that gives 6 over 5x fixed. So dy dx equals dy du times du dx. dy du 1 over u, du dx 6 over 5 x to the power 5. 1 over u. This is u. The reciprocal 1 over u actually is reciprocal of u, so that gives 5 over x to the power 6. 6 over 5 x fifth. Let's see, 1 over u. So with 5 over x to the power 6, 6x fifth over 5. So this cancel, right? And we have a 6 on the numerator. We have x in the denominator. So it is just 6 over x. 6 over x. Double check. Yeah. Next. Question number 12. Derivative. 切入 again. Y equals ln u. Decompose the function is very important. Y equals ln u. U equals the argument 5x squared minus 7x plus 4. 5x squared minus 7x is 4. Okay. dy du 1 over u, du dx 10x minus 7. Okay. The derivative of x squared is 2x. 2 times 5 is 10. 10x minus 7. 4 is a constant, so 0. And dy dx equals dy du times du dx. dy du 1 over u, du dx 10x minus 7. So we have a 10x minus 7 in the numerator. We have 5x squared minus 7x plus 4 in the denominator. That's the answer. Five x squared minus 7x plus 4. 10x minus 7. Double check. Next. Question number 13. Suppose that in 1648, a man bought a diamond worth the equivalent of $19. Suppose that the man had instead been able to put the equivalent of $19 in a bank at 3% interest compounded continuously. What would that $19 have been worth in 2002? Okay, so this is just to find the future value of the investment when the interest compounded continuously. The formula is A equals P e to the power RT. Original investment, in this case, is $19. Our annual interest rate, T is the number of years. A is the accumulated balance to the future value. So here we need to figure out the number of years. It says from 1648 to 2002. This is what I do, okay? So 1648, you start with the 1648, then you that is 352 years away from 2000, right? And 2 more years you have 2002. So that's what I do. Or you can just use 2002 minus 1649 or 48. Yeah, let me double check. 354. Okay. You should write it down your scratch paper, and then we can use the calculator to process this problem. Let me look at the data again. $19, 3%. Start with $19 and multiply with e to the power of 3% 0.03. 3% is the annual interest rate, as decimal is 0.03, times the number of years. How many years that is? 354. 354. Okay. Nearest dollar. Okay. 6 is bigger than 5, so 777,967. Not even a million, but you start with $19, right? You start with $19 and $777,967. Let me double check. $19. The interest rate is not high, only 3%, 0.03. 352 years, 354 years. Okay, and that's it. That's this problem. Next, question number 14. So of an initial amount of 6,000 grams of lead to tin, how much will remain in 180 years? Lead to tin decays at a rate of 3.15% per year. Okay. 180 years. So for exponential decay or exponential growth, you only need to grasp one formula. Okay? Yeah, when R is positive, this is growth. When R is negative, this is decay. We only need to know this formula. P sub 0 is the initial population. T is the future population when the time elapsed by T years. R is the rate of change. When R is a positive, exponential growth. When R is negative, exponential decay. So in this case, we are talking about decay problem, right? Initial amount is 6,000. So we want to know the future amount. The rate is 3.15%. But you cannot just enter 0.0315. Instead, you should do negative, okay? Negative 0.0315. And then times T, how many years? 180 years. Okay, yeah, we can enter that to the calculator. Double check entry 6,180 years, 3.15. 6,380 years, 3.15%. Okay, next, enter decay to rounding 1 decimal place. So 20.7. 20.7. Next. This one is about the pattern, the model. For the scatter plot on the right, determine which, if any, of these functions might be used as a model for the data. I wouldn't say this is linear. This is decay. It looks like an exponential decay. Exponential decay is this one. Okay. The formula looks like a little bit different from my formula here, but actually in essence it's the same thing. They use A instead of P sub 0. They use K instead of R, just different letters. So I'm going to choose exponential decay. It's not quadratic, not polynomial, not logarithm. The reason is not logarithm because it seems to have a horizontal asymptote. Okay, exponential growth, exponential decay functions have horizontal asymptote. Logarithmic growth and logarithmic decay has vertical asymptote. And this picture, this image, doesn't really show a vertical asymptote, but the horizontal asymptote quite obvious. So I would choose exponential decay. And we'll see if it's correct. I think it's correct. This one is exponential growth because k is positive. This is exponential decay because the coefficient of x here is negative. Negative k is negative, while k is positive. All right. Next. Question number 16. Find an exponential function of the form. That's another formula about exponential growth and exponential decay. That models the situation, and then find the equivalent exponential model of the form. This is the one I recommend you to memorize, right? This is a different formula. We need to know the meaning for each variables in this formula. It says doubling time is 4 years. So when this big T is 4, we're gonna have to enter n equals 2, because n here denotes the growth factor, of the population over the time period of big T. Since big T is the doubling time, 4 years, that means over the 4 years, the population will double. So the multiplication factor is 2. So we're going to enter this as initial population 350, 2 to the, and then it has a dot as multiplication, ideally. If not, we can probably use this to mean, oh, okay, yeah, it will give us the multiplication. So initial population 350 times 2 to the power T over 5. T over 4, my bad. T over 4, okay? T over 4. T over 4. Doubling time. T over 4. Okay? That's it. What about the second part? How do we convert that to this formula? 350 T equals 4. T over 4 equals 350 e to the power RT. Cancel. We have T2 to the power T over 4 equals e to the power RT. Apply at n. E cancel. So this brought in front. T over 4 ln 2 equals RT. We want to know the value of R, right? T cancel. So R equals ln 2 over 4. Initial population is still 350. That doesn't change. R here, ln 2 over 4. ln 2 over 4. 4 decimal places. Point 1733. Point. Did I enter the point? Oops. 17.1733. 0.1733. 4 decimal places. Right, and that's it. Yeah, we need to be very cautious, be very careful when we enter the answer. Next, question number 17. Differentiate this function. So what if the base of the logarithmic function is not e? Formula log with base bx. This is the formula, okay? The derivative of a log function with base b is 1 over x. Then we have ln b in the denominator with x. So we can use chain rule. Original function can be written as y equals log with base 4u. And u is x to the power 7 plus x. dy du, use this formula, right? You have 1 over u ln 4. du dx, you have 7x 6 plus 1. So dy dx equals dy du times du dx. dy du dx, I'm going to put on the numerator. and u is x7 plus x, and like that. Okay, let's enter the answer here. Let's double check. And numerator is, denominator is ln7, ln4, my bad, ln4. Yeah, ln4 times. So you can write ln4 to the right of the parentheses. It really doesn't matter. ln4. All right, next. Question number 18. Differentiate the quotient. We're going to use the quotient rule. Let's say y equals f over g. F is 3 to the power x. G is 7x plus 2. F is the numerator. G is the denominator. F prime, 3x, 3 to the power x, ln 3. You know this formula, right? 3 to the power x, ln 3. And G prime is 7. Slope of the linear function. So y prime equals f prime g plus f g prime. F prime g plus f g prime. Can we just enter like that? I think it's okay. I think we can just enter like that. Plus 7 times 3 to the power x. Let's see. 3 to the power x ln 3. 3 to the power x ln 3 times parentheses 7x plus 2 plus 7 times 3 to the power x. I think this would work. Question number 19. Graph the function, identify the domain, range, y-intercept, and state whether the function increasing or decreasing. Let's see this problem. Graph the function. Okay, so we have 4 answer choices here. Let's look at this way, okay? Let me firstly write down the function here. Y equals negative e to the power of a negative x over 6. We can write this as negative 1 over e to the power of x over 6. Okay? So let's see how when x approaches past infinity, okay? When x increases, when x increases, x over 6 increases. Let's do this way. When x increases, x over 6 increases, right? And e to the power of x over 6 increases, getting bigger and bigger. But you take the reciprocal, 1 over e to the power of x over 6 decreases. Okay, because numerator stay as a constant. When the denominator is getting bigger, the fraction getting smaller. However, you have a negative, and negative is increase. Does that make sense? So the function is increasing. Since the function is increasing, B and D are out. We're going to look at A and C. So this function should have an asymptote. Let's see what's the asymptote. When x approaches infinity, when x approaches infinity, x over 6 approaches infinity, right? Let me show you this way. We're looking for asymptote. When x approaches past infinity, x over 6 approaches past infinity, e to the power of x over 6 approaches infinity, but 1 over e to the power of x over 6 approaches 0. Okay, because 1 over infinity is 0. Okay, and negative 1 over e to the power of x over 6 also approaches 0. The positive or negative doesn't really change the limit. So that means when x approaches infinity, y approaches 0 from the left. From the left. So y equals 0 is a horizontal asymptote. Horizontal asymptote. Which one has a horizontal asymptote? Y equals 0. This one. All right. This one, obviously, horizontal asymptote is down below the origin. That's what I see, but I can make it bigger. Oh, hold on. No, it's not that. Hold on. This seems has a horizontal asymptote 0, y equals 0 as well. Let's see. This one is concave down. Okay, let's see the y-intercept. So let's see when x equals 0, what is the y? When x equals 0, y equals negative e, negative 1 over 6 times 0. So it's negative e to the power of 0, that's negative 1. So the y-intercept is 0, negative 1. So the curve cut the y-axis below the origin. Below the origin. I would still choose this one because this function, if I make it bigger, sorry to make it bigger. The y-intercept is above x-axis. Y-intercept is not negative 1. This one is. This one is below x-axis, okay? Yeah, also remember when x approaches infinity, y approaches 0 from below 0, from negative. From negative. So it should be this one. Okay? It's this one. It's increasing 0, negative 1. Okay. The domain is all real. There's nothing to restrict the value of x here. X could assume any real number. Domain is all real. Negative infinity, positive infinity. What about the range? Range, as you can see, is below. Look at the graph, below x-axis, right? So all negative. So it's going to be negative infinity to 0. 0 is excluded because y equals 0 is the asymptote. You will not ever touch or cross over. So it's a open interval, all negative. The y-intercept is 0, -1. The function is increasing. Okay, once you have the graph ready, you can identify the domain range intercept. We get an intercept earlier, y-intercept, and increasing or decreasing from the graph. Double check entry. Okay, next. Question number 20. Domain of the function. Okay. For logarithmic function, y equals log with base b x. Okay, this could be more complicated than just x. This part is called argument. The argument of a logarithmic function has to be always strictly bigger than 0. Okay, so to find the domain for that log function, we need to find the argument for that function. The argument of this function is 7 minus 2x. We make this strictly bigger than 0 and solve this inequality. We have -2x bigger than -7 and divided by -1. Don't forget to flip the direction of the inequality symbol. We have 7/2. Okay, x is less than 7/2. So the domain is -infinity to 7/2 open. Type your answer in interval notation. Okay. We should always read the information in the parentheses. If you don't, a lot of times you make mistakes. That's the reason I recommend you practice review multiple times, at least 5 times. Graph the function, choose the correct answer. So the domain is -infinity to 7/2. This one domain doesn't work, right? The domain is to the right of the 0. This one doesn't work. It's either this one or this one. From -infinity to 7/2. It has to be this one. From -infinity to 7/2. This is 6. 7/2 is 3.5. It's around here. And this one, this is a 2. It doesn't look like correct. So I would choose this one. Yeah, simply using domain, we are able to choose the correct graph. Or you can try to plug in x equals 0 to find a y-intercept. If x equals 0, then y equals ln 7, right? What is ln 7? Ln 7 is around 2. This is around 2. So, and this is when x equals 0. It doesn't even show. But from the trend you can see it's going to be negative. So this one is incorrect. Has to be A. Has to be A. And those two domain doesn't match. All right, is that all the parts? Okay, next. Question number 21. Differentiate. This one is a simple. Differentiate. This one is also very simple. You should not have any problem process those problems. This one, how much money must you invest now at a 4.2% interest compounded continuously in order to have 10,000 at the end of 6 years. Okay. So I can show you how to use the calculator. Okay, use the calculator. You can start with your financial goal. You want how much money? 10,000. 10,000 is your financial goal. And you're going to divide it by a denominator. I use a parenthesis just in case, just to, make sure the structure is clear. And it's compounded continuously. So we're going to have a e exponential expression here to the power of annual interest rate 4.2%, 0.042 times 6 years. Oops. Oh, I messed this. I mean, like this. Then 0.042 times 6, and then close the denominator. All right, do you guys remember if you start with the principal, you multiply this factor, and you will have the future value. This problem, you have the future value, your financial goal. You want 10 grand in 6 years. So you start with your financial goal, future value of the investment, and you're going to divide it by the factor. It's the only difference. This can be called as the discounting factor. We actually are discounting now. From future value to current value, present value, we're discounting. From present value to future value, we're compounding. Yeah, when we are compounding, this is called a compounding factor, or discounting, this is called discounting factor. Since we're looking for the present value that we need to achieve the financial goal in the future, we are having a discounting problem. So from the future value divided by, you enter the future value, 10 grand, and then divided by the discounting factor, e to the power 0.042 annual interest rate times 10 years. 4.2%. Okay, that's correct. Let's see. Nearest cent. That makes sense, right? You want a 10 grand. Well, 6 years ahead, you have to put in 7,000 each, like almost, yeah, $7,772.45. That makes sense. Question number 24, differentiate. 13, this type of problem is very straightforward. You really shouldn't mess up those problems. And multiply with ln13. Question number 25. Same as earlier. 3 ln7 times e7 to the power x. Okay, or I think if you want to write ln7, you're going to write 3 times 7 to the power x and then times ln7. That's totally fine. 3 is original coefficient, stay there. And the derivative of 7 to the power x is 7 to the power x multiplied by 7 ln7. So let's see if we make any mistakes. Question number 18. We mess up one question here. Oh, I messed up a sign here. Minus 7, yeah, minus. Let me look at my original work. No. I couldn't find where the problem is. It's question number 18. Oh, 7x. Question number 18. This one. Oh, Jesus. I made a very big mistake here. I apologize. It's a quotient rule here. How about let's redo this problem? Probably doing too fast. F is the numerator, 3 to the power of x. G is the denominator, 7x plus 2. And we have f prime, g prime found. And the y is not a product, it's a quotient. So f prime g minus f g prime over g squared. So g squared is 7x plus 2 to the power of 2. F prime, 3x ln 3 times g, 7x plus 2, minus f 3 to the power of x times g prime, which is 7. So we should have this and then enter to the cell. Yeah, I apologize again. Yeah, as you know, human being make mistakes is totally fine. Yeah, so just be very cautious. I was rushing, which is not good. Knowing this problem is applying quotient rule. This is the formula for quotient rule. Yeah, I made a mistake, use the wrong formula. I corrected the problem here. Right? That's the only one. Okay, not too bad. I'll see you next review.